right, Steve Nellis here from the information in the offices of Founders Fund here in San Francisco to talk about automation and how it's going to change the way that we live and work. And I've got with me two awesome entrepreneurs, Brian from Emerald Therapeutics and Nick from Plethora. And I guess before we get started on the discussion, maybe just like a minute or two on what each of you guys do, you know, how the company got started and the problem that you're trying to solve.
Do you want to go with me first?
Yeah, sure. Let's go.
We have a more, I think, circuitous route than you guys can. So we actually started as a therapeutics research company a very long time ago now. And there was as much thought in the company about what we were doing as how we were doing it. So the therapeutic stuff is still stealth. It's a very long-term thing, but we built this thing along the way we call the Cloud Lab now, which was basically the ultimate tool for doing research, where the vision was how little manual lab work do we have to do? Can we get it to the point where we're really just giving instructions via the computer that describe how the experiment should be run without any ambiguity? And then that's something we could essentially automate or industrialize, so we could do it at scale. And that became a standalone product in itself and a big focus of the company.
And I feel like it's interesting how much similarity there are between our companies. I mean, so essentially the biotech version, ours is sort of the old school manufacturing version where, you know, our customers are people who are making prototypes for, you know, like physical production of things. So anything from, biotech robots sometimes, flying cars, all sorts of stuff they make, they need to prototype it very quickly. And usually that involves a phone call to like an old guy in a shop somewhere. We've basically automated the whole process of the pricing, the sort of feedback on the part, and then also the factory will automatically configure itself and then produce the parts you want. So our whole business is thinking about, like, when you engineer something, how can you give sort of superpowers to the engineer or the designer to really like express themselves in the physical world? And we started with the production process. There's many different things around like the interfaces and infrastructures that you need to do to make that possible.
Yeah. So first thing I'm curious about is what were the technical challenges or things that are new or different technologies that you were either able to integrate or build that weren't around before that allowed you to do this, and why hadn't anybody done this before? I mean, you know, the biotech industry in particular, right? I mean, it's one of the most expensive industries there is. It requires all this upfront capital. A lot of it goes into clinical trials, but there's a big component that revolves around testing. Like, there's a lot of monetary incentive for people to get this right. So what were the things that fell into place that enabled you to sort of put these systems together, from a technical perspective?
So in Emerald's case, there are really two big kind of innovations. One we inherited, and the other one we had to build on our own to get to the point where this was a possible product to build in the first place. So one was in many ways we inherited some of the robotic hardware from, there's a subset of biotech called high throughput screening, which is where you take giant libraries of compounds, 500,000 million compounds, and you screen them through the same assay like 1 million times to try to get early leads for what might make a good therapeutic or something. And then it has to get optimized by a further process.
Okay.
But that start point was just very repetitive. Conducting those assays was just basically like it's liquid handling and then incubation times and then some kind of imaging usually at the end or some downstream assay that works at scale.
Okay.
Right? And so we inherited a lot of that hardware, and a lot of it was just it was doing the right physical motions that we needed. The problem was it was designed to do the same thing 1 million times. And we needed to change it to do 1 million things once.
Right.
So the big layer that we kind of had to add was this idea of having you call it a programming language with some sort of control flow, a way to express what you wanted to do in the lab and give it an instruction that can get converted through a layer of software to what eventually would be commands on the robot. So it gets all the way down to the hardware level at the last second, but that's not the thing you want to expose to the front-end user because you want to express your experiments in a very high-level language, the way you would talk to another fellow scientist about how to run something, and then it figures out how to fill in all the blanks of, okay, this motor is going to run at this force for this long, and it's going to draw this up and move that.
Okay. So all of that, essentially all of that, you had to rip out all of the middleware. And,
it was a lot of software. There's some hardware when we had to make parts occasionally, and it's useful to have an ecosystem out there to go to for that. But I'd say it's like probably 80-20 software, hardware.
Okay, okay, interesting. And were there any software breakthroughs that allowed you to offer this as a product too? I'm curious about that. I mean, I assume you're using some of the standard things that everyone's using now in terms of cloud computing.
Yeah, definitely. Like everything lives on AWS, so we take advantage of all the modern stuff there. I mean, we're using a lot of modern open source things. So the platform itself is delivered on NWJS, so it's this thing that lets us be cross-platform very easily.
Yeah.
Much like what Spotify does and stuff like that.
Yeah.
And we take advantage of. We do some high-performance computing, parallel computing on the cloud, and we use Docker for that. So there's some tools that we take advantage of there. And then the big one is we've really taken advantage of this thing called the Wolfram language.
Oh yeah.
Which used to be called Mathematica.
Yeah.
So not surprisingly, math lives behind most of the science stuff that we do. So inheriting all of that mathematical toolkit and the data analysis and there's like image processing, plotting, all kinds of bottom level functions that we call on the higher level to do stuff. It's been very helpful.
Cool. Nick, how about you guys? What were the things that you were able to integrate or that you were able to put together to make this happen?
So I guess the sort of shoulders of giants we stand on are kind of like, on the one hand, you have the design software. So 3D design software over the past 10 years has gone from pretty low adoption to nearly universal adoption by like professionals. So that's one thing. It's okay, there's an install base. It's almost like the browser. Enough people use the browser, you can start doing stuff with it. And then the second one is the actual hardware itself, which has been computer programmed for maybe since the 60s around that. And then there's a language from the 60s that looks like it that you program this thing in. And that's sort of where you start. So I can buy equipment that like this really shitty language and interface exists on. And then we had to kind of like borrow and steal our way into the codes to get the API on that machine. And then the big thing that we do is normally the person who would program that machine is a human, so a machinist. And so we sort of have to replicate their brain and say like, how are you going to do it? So a big part of that is taking the design from the design software, making sense of it and saying, how would we make this? And so our whole system, that's the novel thing we build on. The shoulder of giants in the 3D world, but we have a lot of novel algorithms that do that analysis. It makes a whole like kind of plan, and then it'll give individual instructions. So like, okay, take this cutting tool and move it this way, and all the different things that a machinist would have to design and program. We automatically do like kind of like a compiler for software, but for hardware.
And so in both cases, you guys are kind of like ripping out. You're taking these machines that are essentially dumb, right? Ripping out the middle of them, and you get machines that are dumb, and you got some good interfaces over here, and you're ripping out the middle and kind of being like, let's do something that lets this thing that everybody uses, whether it's design software or Mathematica, which is these universal tools, and like how can we actually use them to manipulate these dumb machines? So if that's what you're doing, is this even, is it automation yet? Are we to automation yet, or are we just to augmentation at this point and getting stuff out of the way?
It depends from whose point of view, right? That it's automated, right? I mean, you asked the question, is Uber automated? Not if you're the driver, but definitely if you're the user who's pushing the button. Right? So from the standpoint of our users, it's like the ultimate conclusion of automation on the back end, where they just type in, this is the experiment I run, and then they get the result they want. On our end, we have to build mostly software, but some hardware to try to make that as automated as possible. So that our whole facility is 15,000 square foot facility. It takes 2 people to keep it running 24/7 right now. So it's not like lights out, but there's still 2 people running around like trafficking stuff to get it rolling. So.
Yeah, so 2 people. And how many people would that be in a traditional environment?
For the number of experiments we clear, at least 10 to 100 times that, probably.
Okay. So
in terms of but it's a different set of people too, because one of the things we always have to get away from is that operations team, which is that's the group that handles the logistics of keeping the samples flowing, is not the same as in a traditional environment. You might have a hierarchy of scientists where there's like PIs at the top, and then there's a bunch of staff scientists who work for them, and then maybe there's some lab techs beneath them. But they're all adding sort of scientific contribution up and down the stack. They just they're focused on a different level of the problem, usually. In our case, we just cut directly to it's full control over whoever's entering stuff in. And operations is all about logistics. It's all about getting things to move quickly, but it's never adding any scientific knowledge to the whole platform.
So is that a job that more people can fulfill? Is it a lower level job than say being a lab tech would have been? Is it a comparable job? Is it?
It's well, in salary, it's a little bit better actually, but it's like it's a different job. We call it like our analogy when we go to hire people to describe what it's like. It's like being the first responder of science. We say it's like being an EMT, where your job is just about quickness, efficiency, never making errors, and moving things forward. But you don't want to be making start surgery on the floor like right there. You ship it up to there's another layer to handle that. So our operations team is never doing things like pipetting or anything like that. It's always a robot that's doing that, but they're handling usually the coordination of traffic between all the robots to get things running.
Okay. Interesting. And how about in Plethora? I mean, are there, you're moving that machine operator from the loop that usually translates what you get from the CAD design software to the machine? And if so, what kind of a productivity boost are you getting out of that?
Sure. I mean, it's funny. Like we have very similar dynamics where there are operators on the floor that kind of like load things and like more like physical stuff that eventually will become robots. Yeah. But now people are more flexible, so you use them that way. But the big thing that we automate is the programming. So what would take a human maybe a day or two to do, we do in a few minutes of server time. Right. So that's like the difference in sort of productivity between that. And so that takes like nearly all of the cost of setup away. Which is why people can just like spin up and make one thing, and it doesn't cost them like it would cost to make 1,000 things traditionally. Right. Yeah, but it's true. The operators are differently trained. Like our entry-level people need to know nothing, and then other people need to know a little bit more to like maintain the machines and stuff. And we kind of actively bring on entry-level people, send them to like the school, and we just kind of onboard them as like a conveyor belt of like, okay, raw material that has no training, and then just keep moving them through.
Yeah. Do you have any sense yet of like? It used to take this many people to run a prototyping facility and handle this many orders a day or a week or a month, and now it will take this many.
Yeah, it's a good question. I mean, I think
if you're looking at 10x to 100x at Brian's company, do you have a number?
Yeah, it's at least 10x, but we don't have it hasn't fully gone as mature. You guys are ahead of us. So
what are people going to do with that? What are new things that we might see come out of these industries, life sciences,
sure.
or physical things that we wouldn't have gotten before? I mean, and I guess the analogy I'm thinking about here is with software.
Totally.
Amazon Web Services, which you guys are both probably using, has totally changed the process for how you create software in terms of not having to wait around for weeks to provision new hardware. Right, you get it right when you need it, and it's made different things possible. It's made it possible to fail faster and pivot to a different idea. Totally. It's totally changed the way that the software business works. And I'm just curious if you guys have any insight yet. I know it's very early, like you're just early stage of development. But are you seeing anything that customers are doing with this that gives you hints about what it might allow them to do, analogous to how cloud computing changed the way we put together software and information services?
I mean, I think the large thing, there's like kind of two parts, at least for us. Like one is by having the sort of infrastructure so flexible, you can do lots more iterations in the same level of time. So you can have either a better product or you can get to market faster. Mm-hmm. That's one thing. On the other end, it's sort of like building these interfaces that make it so people don't have to know the exact process stuff. So in the manufacturing world, there's a process called DFM, Design for Manufacturability. And that's like every little thing in your product is evaluated to see if it'll work, at scale or whatever thing you want to do. Yeah. And so by analyzing it automatically with our interface, we're able to let people do that in real time, where normally that might be like a couple days of you send your file to some guy and he reviews it, and then you have a call tomorrow, and that is instant. And so if you don't know how to do a given process, our thing will say, start just trying to design it, and then we'll say, hey, that's a problem, here's what's wrong, and here's how to fix it. So it's almost like a learning tool. And so you can actually be more flexible. Like right now, these industries are very siloed. There's like a metal engineer for just sheet metal, and just machining, and just plastic. And it's like, what if you could do all of those things? Yeah. You can have like superpowers that like one or two people can say build an app. They can't build a car right now. What if you could do that? And only a few people could start entering markets that now require so much money up front. You just lower those barriers of entry of the design and prototype to get to something that works. And then, of course, scaling, because the infrastructure is so flexible, then just happens as you need. So it's a lot less sort of cost of capital required to do anything.
Yeah. Brian, what about in life sciences?
I think the kind of like emotional feeling among the users is some combination of like relief and freedom. Science is one of these things that's ironically, it's supposed to be a very intellectual activity. I think every first-year grad student comes into grad school, bright-eyed, bushy-tailed, and like, I'm going to do science, and you do that when you first get there. Like, my experience was, I designed for the first, I would say, month to 2 months. I laid out everything that was going to be in my thesis. So 5 years of physical labor got laid out in this 2-month period. Ended up being this 500-page monstrosity, several papers out of that. But to get to that realization meant, very long nights in the lab, just doing sort of mechanical labor to get there, and then dealing with inefficiencies in the mechanical labor, problems with the system, tons of troubleshooting on the equipment, stuff that was kind of like below the level of where I was trying to advance. It was like pay to play. So getting your thermocycler to work, or getting your HPLC to not leak during a run, those are valuable things you need to do to get data out of your system, but it's not, you're definitely not advancing the science by doing those things. You're just getting to the starting line so that you can then do the next thing.
This is a tell, I think. Like, you see, I was having a conversation with my friend, and he was saying, he's like head of engineering at a like kind of crazy company, and he's like, give me 2 great software engineers, but give me 10 mediocre mechanical engineers. And the idea is that like there's not as much automation in mechanical, so like sometimes it's just like find the bolts that work, and that's what you need. And like you don't need this champion, sort of mechanical person, where software tools are way automated, so you do want really good people who can really make use of the tools. And yeah, but scientists have to do all this manual like shit work is like, really unfortunate that like their brain power has to do this, and think about how to fix that thermocycler or something. It's really annoying. So I think any industry where you see that, it's like, oh, okay, yeah, that's obviously going to stop.
Right, for automation, we basically have vastly overqualified people who are just messing around to get stuff to work. That makes a lot of sense. Another thing that occurs to me too, that's common to all these processes, is that the best you can do is not screw them up. So like, and this was actually something that Jeff Lawson, the CEO of Twitter, or Twilio, was saying in an interview that I was reading the other day about when you should build versus buy software, and he said if the best thing you can do is not screw it up, then you probably should just buy it. And if the best thing you can do is some sort of actual improvement over it, then you should build it yourself. And it seems like there's an analogy here of what things to automate. These are all processes where the best thing that the user can hope for is just getting it right. You're not, like, as a scientist, you're not adding any value to the process by
getting
making
gel
sure the
to
machine,
run or something,
making sure the machine doesn't leak is not like going to cure anybody's grievous illness, but it is necessary. And so if you can automate that part out for people, it seems like it makes a lot of sense. Is that how you guys think of it?
I think that's definitely the first level, is just taking away barriers to entry for sure. I mean, there's also just a physical cost constraint of, like, the average first round financing for a biotech company is like $7 million, and the software world is like $1 million. So it would be nice for the same amount of capital to get 7 times as many biotech startups. You can imagine that would propagate down the line and have a pretty good effect on the ecosystem. But then there's also, from the highest level, I think it does something it corrects a big kind of growing problem we've had in science, which sometimes gets expressed as reproducibility, sometimes gets expressed as like this frustration with grants or trying to get very, very large labs. I think some of the most interesting insight I had there is I was lucky enough to, at some point, get introduced to Sidney Brenner. He's one of the founding fathers of molecular biology, Nobel Prize winner. And so, we met a couple times, and having lunch with him, I got to ask him questions. I'm sure he's tired of hearing these sort of things. But the thing I really wanted to ask him is, what does he lament is most different today than from back then? Because it was like the heroic age of molecular biology in the 50s and 60s. We made this very rapid progress very quickly. And he had a lot to say. Some of it was focused on the way grant funding works. But one thing that I really keyed in on, which I think had a nice parallel here, was that he said back when a lab was very simple, so when they were doing research, a lab was like benches and glassware. So anyone who had one, it was pretty much the same as someone else who had one. There wasn't much to it. He said the biggest struggle he had was he was trying to get a dishwasher during the war, so like the metal surplus to get the dishwasher was like a big deal. And that was like the most sophisticated piece of equipment they're trying to get. And when that was the case, his argument was that science was very top-down. That the business of a scientist was to come up with the most elegant set of experiments to get at a truth. So they would start with a high-level question, something like, How does the information make it from the DNA molecule to the protein molecule? Very important. And then your job as a scientist was to come up with the no-loss, minimal way to get to that truth and definitively say that this is the path it takes and it doesn't take these other paths. It's this technique called strong inference. They used to do that. But his lament is like, nowadays, we're still trying to do the same objective, right? We're still trying to move science forward faster. But we've become, instead of being top-down, we've become very bottoms-up. So because the thing has become so resource-intensive, and we have all these tools that they wouldn't dream of back then. We have mass specs and NMRs and these very expensive, $500,000 plus machines. We have teams that are enormous, so they're 10 times at least the size of the teams that they used to be. And with that, I mean, he said this kind of as a pejorative, but he's like, the scientists now, the big ones, they look more like CEOs than they did back in our day. It was a bad thing for him to be a CEO. He's like, because you have to manage all this resource. And so the thing of science nowadays, in his mind, is about taking from the bottom. I'll say, I have this resource, I have these pieces of machinery, people with this expertise, I have this much grant money. Okay, what can I do from that would advance the science? And it's trying to get at the same goal, but the argument is if you come from the top down, there's no waste. It's only the minimal set of experiments you need to do to advance the thought. From the bottom, it's a lot of towards this, towards that. Are we sure we're making progress? Papers that don't get referenced. Stuff that's a partial solution that doesn't really tell us that much.
So that's a neat thought. How do you guys solve that?
So by going to a world where there's one industrial resource, right, to produce all the experimentation, whether you're Sidney Brenner with his 30, 40-person lab, or you're a first-year graduate student, you're connected to the same resource. So the second you walk in there, we've pushed aside all of the grinding of handling I have this smart equipment in terms of cost, in terms of getting the thing running, in terms of all the troubleshooting you have to do in advance. The staffing is no longer an issue. You don't have to hire 30 people to execute on your ideas. You can do it by yourself. And that allows you to go back to a focus where it's a much more metacratic thing, right? It's based on, is this experiment actually advancing us in science?
Right. So you don't have to worry about, well, I can't ask this question because I don't have 40 people.
Right.
Right? You just think, well, if I can massively parallel run these experiments, I can ask the same question.
Yeah, and you hear this frustration across the whole ecosystem, right? You talk to entrepreneurs, their big stressors are, how do I get the data I want? And it's going to require getting this machinery and getting access to these samples and getting this many people. And if you talk to PIs, it's very similar, like, well, how am I going to get access to enough grant money to do this thing and enough people to get this thing to move forward? And even in pharma companies, it's a lot of, well, how are we going to get 40 people to pivot around this idea? I have to go convince 40 people that it's a good idea to do this kind of radical thing. That's a very difficult thing to do.
Interesting. Anything similar with Plethora? I mean, what are some of the challenges there? I mean, one thing it seems like you're really focusing on is being able to connect put the designer and take out the process and intermediary steps and put design right next to design right next to the actual fashioning of things.
I tend to see it as like there's a continuum of engineering, sort of like expressivity or conservatism. Like on the one end, you have like computer science where it's like every minute you can iterate, all the time, and you're expected to. On the other end, it's like civil engineering. You get one bridge, and if you mess it up, then you're fired, And that's very conservative in there, and we use methods from 50 years ago to do that. And then that's sort of how it goes is like, civil, mechanical, electrical, and then computer science. And so sort of what we think about is like, how can we look at computer science, which gets to iterate faster, and its kind of development world lives in the future, and how do we port all those analogies to the other spaces, And so I guess biotech, I don't know where it would be on that. Maybe it's like mechanical, and the experiments usually take a long time, and they're kind of expensive. I don't know, but it's somewhere on that conservatism, and I see it as our job to make hardware as easy as software. So if I can, right now the limitations of software are just, hit a button and it works. That is not possible in hardware, maybe ever, but if you can get faster than you can write the code. So in our world, it's like, can you CAD things faster than the machines can make them? And we're actually almost there at Plethora where you can we can beat them. Like they can't design parts fast enough that we can't make them and send them to them by courier fast enough. And at that point, you're pretty much, okay, it's just your brain, to be able to learn the tools. And then beyond that, that's like the fulfillment. It's like, to linking it to designers, like how can you make a designer really know the whole space, What we're used to in, very basic way, like Amazon will say, maybe you need this, you bought the remote, do you need the batteries, or something like this. Such doesn't exist in industry, and it's actually a lot of problems where a lot of your job is just looking through catalogs. And understanding, I need pneumatic fittings that have to fit this pump, and you don't know. And some questions are more like semantically generated. It's like, how would I move the shovel on this thing, And you don't know. You could use all these different methods, and how do you decide? Even down to the methodology of engineering, I think, has to change. So, like, sort of apropos to the topic of work, like, all these methods of work, like design thinking and Scrum and Agile and all these things, actually, are, to me, very relevant of how do we, at Plethora, I think, how do we build a hardware world that has, like, the ultimate way of doing it? Because we have this, as tool makers, the ability to really have this giant lever on humanity. You know, if technology is one of these huge things that can move humanity forward in our standard of living, and our sort of expressivity of the individual, and to, like, take the sort of freedom and capabilities you have and express it into the environment and to make everyone's lives better, hopefully. By making that faster and more expressive and a better solution, shouldn't we as tool makers be able to just, everything? And that's, sort of what drives me to do it. And I think that sometimes it's like, how do we even know what problems we need? That's one question. Then how do you know, okay, this problem, how do you know the problem space? How do you think, okay, this is how I'm going to solve it from knowing that space? How do I implement said device, poem, like whatever you think is the way of solving it? And then actually, how do you make it a sustainable business or whatever? I feel like that's the thing. The economy just does that. And by producing these solutions, then we get a better GDP and, individual productivity and everything that should drive our standard of living. At least that's kind of how I think of it.
You said something very interesting in there that I think ties into historic parallels that we can draw off of. It was interesting that when you stacked it up from, like, mechanical engineering down to CS, electrical engineering was closer on the iteration side.
Totally,
CS,
yeah.
Which is interesting because if you think of it from just like a purely tooling perspective, it seems like, CNC's got to be easier than making a microchip, but because the ecosystem and what Taiwan Semiconductor and virtualization has done, you want to talk a little bit about, like, how
it's interesting. We
look at them constantly as comparable.
This is a good thing to talk about. Why is it actually probably, like, harder to prototype a part than a chip? Right.
And I would say that, like, most electrical engineering is actually not making the chip, it's making the board.
Yeah.
So those are, like, the two problems. There's a lot of stuff about, like, antennas and whatever, but, like, really you're probably making boards, and the chips probably even exist, So, like, one, you have FPGAs, which are, like, reconfigurable computer chips that you have for prototyping now. So you don't even need to make a chip until, now you can get a die share, meaning, like, a really low kind of cost setup for making a new kind of chip for, I think, like $50,000 for basic technology. So that's, like, amazing. You can make a chip for $50,000, but you can make boards for, like, $200.
Yeah.
So and you can, if you ever try to make any of this stuff, so code, you just do this and hit enter. With electrical work, you can kind of just, like, solder some chip together in an hour and it works. So a lot of labs will have, like, say Arduinos for, like, a very simple prototyping board, and you just plug some stuff into it, and you know how these sensors work, and it just works. Mechanical isn't like that. I remember making our early robotic stuff at Plethora, and I made it on manual machines because I couldn't, like, afford to get CNCs before we had any funding, and so I was just, like, pounding that shit out. And it's like, God, my grandfather was a machinist, and I'm like, how did he do this for his whole life? On these manual machines, and in hardware, even CNC is the same way. It's like it's so much bullshit. Like, I prefer to just do it manually. Honestly, if I don't have Plethora, now I can actually send my shit to Plethora. By the time you get that punching
stuff into this, like, '60s interface, you're like, I'd rather just actually move
bandsaw. Yeah, just like, it's like my girlfriend wanted some art thing, and I was like, okay, I'm going to make this art thing. And I was like, God, this is taking forever, And it was, like, slightly out of the spec of what Plethora could do at the time. Now we can make it. So I'm like, okay, this is so easy now. It just appears. But before it took all day,
Yeah.
But so your question was, like, why electrical is closer to CS?
Well, I was saying, even in the virtualization space, like, there is this push-a-button thing with something like Taiwan Semiconductor or Global Foundries.
Yeah, sure.
You tape out and you send them a chip, and it's an elastic product. You can join a shuttle and get, like, one chip if you want.
Yeah.
Or scale it up to 10 million units, and you don't need to do any of the grinding. It's
True.
just producing the thing.
And the file is a big thing too. So the layout of a chip, and, like, I guess the VSLI or HDI or any of these or HDL, the rules, like how the circuit of the chip works, is portable. You can take the same thing and flash it on an FPGA, this, like, reconfigurable chip, and then you can take the same thing, go, okay, cool, that worked. Go to Taiwan Semi and say, make 1 million of them, And it's an amazing thing that we're able to do. And mechanical actually doesn't work that way. So in mechanical, the CAD file you might 3D print or machine as a prototype is not the thing you'll injection mold or cast as the end product. And everything has to be redone and optimized, and that's a lot of human twittering on various things to do, and it takes forever. And unfortunately, mechanical does not have two things like chips or boards. It has hundreds of different components, and everything you look at, like, this is just blow molding and injection molding for some little water thing, and who knows the other equipment needed to, like, make the label and everything else. Boards are easier than that. It's just, okay, fiberglass, copper, put some shit on there. It's like, there's a million companies that do that.
Are you ever going to get to be able to, so right now you're solving the problem with the prototyping. Any hope for the rest of that in between prototyping and manufacturing?
Oh, totally, yeah. So there's a few things. Like, you start in prototyping for us because that's where the pain is. Like, people really need fast iteration. For the rest of production, maybe a couple weeks is fine,
Yeah.
But when they need to tool up, though, meaning like they need all the custom kind of hardware to make your custom hardware, it's kind of meta, we actually would help make that. And then it's like, well, how do you go from production over to short run? Some companies might make 100 objects that reach $1 million. That's actually more like our customers now, because they're like a bunch of custom robots or flying cars or whatever. They're very expensive. They're not, dollar store junk. That's another kind of process would make that. But you can help people tool up by making hardware easy. And then, likewise, you said you buy parts for your stuff. So,
Exactly.
I'm really happy that we're not making cheap shit in the dollar store. I'm happy we're making biotech parts and robots, and that's what I want to help in the future. We don't need some future landfill to flow through my factory. I prefer to not do that.
Quote of the day: I don't need some future landfill to flow through my factory. Well, I wanted to. I want to push you guys a little bit out of your comfort zone and do the journalist thing and bring up the social implications of all this.
Mm-hmm.
We talked a little bit about productivity. Brian, you mentioned Uber, and the big kind of meta theme these days is, are the robots going to come take away our jobs? There's a lot of alarmism out there, but I do think there's a serious discussion to be had about the social impact of this. When you guys think about building these businesses, what's your take on that? I mean, is it even the place of the entrepreneur trying to build one of these businesses to worry about it? Do you need to have a voice in social policy? So let's say we do make it much easier we do expand access to designing physical objects or running experiments, but who has, who's got the opportunity to access those things? Who's going to make the money off of them? It's kind of the capital versus labor stuff. So as you guys are going about your thing, what are you thinking about this issue, even if it's not directly pertinent to what you're doing right now today?
No, it's definitely directly pertinent. I mean, I spend a tremendous amount of time thinking about it. This isn't a job that you pick because it's like a sound, rational choice from a greedy perspective of you're going to be immediately happy. You have to work your ass off, take extreme risk, and deal with a lot of pushback. But the thing that I think you hit on is when it comes to the ethics of it, right? Because we think very carefully about what are the ethical implications here? What are the things we need to be thinking about in the long term where we're aligning success of the company with the world we all want to live in as citizens, right? And I think the key thing you said there was it's about access, right? Because if you try to draw some larger historic perspective around what we're doing, right? If automation in general can go all the way back to stuff like the Industrial Revolution, and there we saw factories for the first time making parts, but that was the biggest, I think, kind of thing that makes this a very different revolution than that is the customizability, is the elasticity and scale. The fact that you can get down to an individual part and one person can control an individual part is radically different than you have to have this massive machinery to get, Henry Ford can build cars and you can have any color you want as long as it's black, right?
Yeah.
You can make the one thing and many, many of them. And we're talking about many, many things once. That changes a lot. And so it does become a question of who has access to it. So personally, from my perspective, I don't know if you thought about this at all, but actually you said something interesting about what people make in your factory.
Sure.
Right? I think a lot about that, because often a very practical question that comes to us is what to do with IP. Right? There's competing voices in the room. There's one group that says, hey, no, you should be agnostic to that. And there's another group that says, hey, no, you should take IP in the winners, and that's how you're going to profit and goal align yourself with your customers.
What do you mean by that? So if you get back up, what do you mean by what should we do with that?
So here's a deal that we could offer that I think is unethical in the long run, so I've decided not to, right? We'll take 5% of your company and give you free experiments for this much in return for something like that.
I see.
This is a dangerous thought from my mind because the thing that makes it so controversial in that is the who has access. If it's this thing that anyone can roll up and with not that much money they can make their own thing, it's hard to think of that as a negative from a societal perspective. We've definitely seen that in, like I said, electronics hardware, where anybody can pretty much make a chip, and that's led to a huge boon in creativity. A lot of what we think about in Moore's Law is that itself. It's just the ubiquity of being able to make computing architecture and put it into stuff. That's been a wonderful thing. Very different. It was much more fraught in the Industrial Revolution, where it was we're replacing mechanical stuff, but there were these few controllers. People call them robber barons, right, who would run these big factories. It's a different aspect. And so taking the equity piece for me is about, I actually don't want to decide what people are doing. Emerald Therapeutics actually has its own therapeutic initiative that it's doing in its own right. But my co-founder and I often describe this as we're trying to So we get through the first thing through, and that's how we saw a lot of the problems that made us build the system we did. But we're honestly trying to build a highway behind us, right? Where anybody can come in, and where any creativity can come in.
Yeah.
And not just like new entrants, but even people at some of the great pharma companies don't have to arrange themselves around only one objective. You could have 10 times as many interesting projects going on at once with smaller groups.
So do you have a vision for this where, a high school kid who's very talented could, hop on via, the SaaS delivered version of your software and be able to start running experiments and get data back?
It's definitely possible. I wouldn't.
Yeah.
I would never
iGEM,
stop anyone from doing that.
I mean,
iGEM
iGEM,
happens.
they
right?
do it. Like there's already like a very basic kind of genetic engineering you can do with iGEM, which is like
Yeah.
the system where you have like kind of building blocks for DNA.
Yeah.
And high school kids do this. So I mean, and they make some not sophisticated things, but certainly in the future leader stuff they will be. I mean, that's kind of freaky to me as far as IP goes, right? I mean, there's a lot more. Maybe the worst you can do with Plethora is make like killer robots or something. With this, it's like maybe famine or pestilence or whatever. There's some amazing things you could do with this kind of power.
Or medicine, right? It's like,
Well, that's
no,
the thing. With
it's
great
about
power
what
comes
you
great
make.
responsibility.
Right.
Yeah, and I think that like IP is interesting as well. Like I guess DNA is like if you got the code, you can do it, and they're like maybe trying to control some of it now. We have similar things where like everyone, of course, wants to keep their design secret. And I've also
how have you
wondered.
thought about that? Have you been presented with the same kind of thing? There's like discussion in the boardroom of like, oh, should you try to get equity in return for working with people, or should it always just be like a cash transaction?
I mean, I think we've never had the like that particular discussion. It's always around like big enterprises, like GE. When I was like, selling to them, they're like, our files never leave our computer unless we know it, right? Like that was a huge.
I get that with
thing,
pharma too. They're very, very
Of course,
defensive about.
yeah.
No one can see this yet.
Totally. And so like, we built our thing so that it runs locally for the analysis, and only when you hit order does it come in. But I'm interested too in like in hardware, and as in I guess biotech, everything's open source. Like you could like sequence some bug and figure it out. Maybe in the physical world, you can just open up the electronics, look at the board, look at the clamshell, and say, okay, that's how it works. And there's machines like industrial CAT scanners that can actually completely rip the internals without even opening it. And in China, we'll just do it automatically for you for maybe 10 grand or reverse engineer something. So I think that like we're almost getting to like MP3 ripping territory with some of these things. We're only going to get more. Yeah, I mean, of like physical products and biological products. It'll be really interesting to see like how, and I guess you could do chemicals too, right? Like you could like gas chromatograph some, chemical thing as well. So you can kind of do anything almost.
We think a lot about that, and like whether or not, like one of the frequent topics of discussion of, we're talking like 5-10 year futures, like should there be a data marketplace to sell data? I mean, and how do we encourage people to publish? Actually, that's one of the big things. Academia already has a way to share scientific information, right? It's like publishing in the literature. So we actually it's really borrowed from like the GitHub model, where we said, all right, there's like a data storage fee that you have to pay, and you generate a ton of data when you work experiments in the cloud, right? It's like terabytes of stuff.
Yeah.
And you have to pay, and so we have to pay AWS to store the thing. But the deal is, we made this pact that said, if you agree to publish your data, which for us just means you release access to anyone, any user can see that data, then we'll pay the data storage fees for the thing.
Really?
Awesome.
Right? Yeah. So we're trying to do it to encourage people, because it's not just a charitable thing. It makes the platform better if you can access all the shared data. If people stay siloed, it's a lot harder to get stuff. And then you will get groups that if they have all the collection of data, that's quite a collection of power too at the end of the day.
Yeah.
So it's nice to get people to sort of share that more.
So 20 years down the line, you're both multi-billion-dollar companies. Are there more jobs in these industries that you're serving, or fewer? And are they better jobs or worse jobs?
Interesting question.
I mean, I think in 20 years, there's definitely more. I mean, I don't believe the thing of like that in the long run, which I'll say 20 years is like pretty maybe midterm, but at least pretty long run, that I am scared of the short term in this. Like I think that there's like kind of a few things going on. You have like the rate at which automation takes jobs, the rate at which jobs are created by new industries or the economy growing, and then of course the rate of training. And so I'm not sure we're as good at training right now as we are at automating things in some ways. Although the unemployment rate in the States does not bear that out. It's still relatively low. Though maybe inequality is going up because worse jobs are happening. So I do think that like maybe people are not able to like realize the productivity they otherwise could have. So I'm kind of interested in like what those equations look like. So on the one hand, like the curve of training, I always talk about like how interfaces can make the machines better. Like the machines that sit on my floor that make this stuff are incredibly hard to understand, and I have like a hobby version. I bring all new employees in like 10 minutes. You can use this thing. Why? It's really not that different. It's like the same thing. So I think that in some ways we as a like economy have to figure that out.
Yeah.
But in the long run, I think we will, and I think there's a lot of pressure to do so.
But can we leave it up to? I mean, can we leave it up to the government to do this? I mean, obviously, there's been a huge gap in training, right? Most of the new jobs and the high-value jobs that are being created are in industries like software and stuff, and companies are out here. They can't find enough people. They're having to basically throw, piles of money into garbage cans and light them on fire to get good engineering talent.
We're seeing the rise of
and at the same time, there are people that jump. So, is there a role that the tech industry needs to play in trying to, develop, close that? I guess we can call it this close gap.
I mean, I think that right now, when I talk to the government, and I just did this thing at the White House talking about the future of work in manufacturing and stuff as well. And, the whole point of their stuff is like, we don't know what to do, and like you have all these trade school leaders around the country trying to figure out like how, what welding is now becoming robotized and, what are we going to do? And, for me, I think that like the trades as an idea is outmoded, and we're not going to have these like 50-year-long professions where you like, you're trained and you die being the same thing. We're going to have to get trained all the time. So at least for Plethora, we have our own training programs because our jobs are novel. And you can take anyone with a good attitude in, and you have to train them up. So I do think that the industry will do some of this. The government seemingly is reactive to industry and is saying, please help us, because they know it's a problem, But I wouldn't say they actually know a lot of solutions, not that I found at this thing anyway.
Yeah. And that's Brian?
Science is like a very unique, I think that's like a much more interesting, like larger discussion around automation as a whole. Yeah. Science is this weird, unique space where, first of all, the trend you're saying, we don't have enough people, is the opposite.
Yeah.
So like if you look in the last...
Too many starving grad students, right?
Exactly. Too many starving grad students and not able to execute on their ideas to get to the point where they can produce something valuable for society because there's giant barriers. So we have this problem where I think in the latest statistics, like in the last 3 years, there's been a 7% drop in salaries for PhD scientists. Wow. So my market value is going down over time.
Wow.
It's very different. And a lot of it has to do with the fact that we can only pursue so many projects at once. And we're dealing with, there's this other trend coming on. Have you ever heard Ibram's Law?
No, I haven't.
Okay, so you've heard of Moore's Law, right?
Yes.
So Ibram's Law it's kind of a morbid joke. It's Moore's backwards.
Oh, okay.
In the biotech industry, if you look at the amount of money you have to spend per approved drug, that exponentially grows. It's every 9 years it doubles, and it's been doing that since 1950.
Yeah.
Right. So the number, if you think of this as like a big pipeline of, the value that's being pulled at the end of the day is what we're providing to healthcare, for the most part, if you're in biotech, right? If that is slowing down, the whole ecosystem has a problem, right? So in many ways, we do get almost no complaints at all, because anyone who speeds up and gets faster to getting to the point where this is like a real medicine that we can actually hand to people, I think people will be quite happy to pay for cures to HIV and these sort of things. And that whole thing helps the ecosystem as a whole, and we all get to move faster. So I think it's a very different industry, because it's not like we're having a problem producing. It's not like we've ran out of ideas or like problems to solve, or it's like, wow, we're like, do we really need another cure to be like, yes, absolutely. No one is saying no to that, right? So like, there's definitely a demand on the other end. There's essentially a vertical demand to pull this, but our inability to supply it is creating the problem. So whenever you lower those barriers to entry, whenever you speed up the entrance to get there, the ecosystem as a whole tends to grow much bigger.
Fascinating. Well, I think that it concludes the amount of time we have today. But guys, thank you so much for joining us, and Founders Fund, thanks for taking the time to host us.